So welcome. Thanks a lot for joining our today's Digital Science for Drug Discovery meeting. We have people dialing in from Iran, from Morocco, from Canada, so very international, but also from Berlin, many people. So the aim of this series is really to bring everyone interested in the topic of digital science for drug discovery together, scientifically, across discipline, in principle, also personally. For the time being, we're still sticking to Zoom. And we will have the format of this series is that we have 2 talks normally, but we also want to socialize, connect people. So after the last talk, please stay on if your time budget allows, and we can chat and get to know each other. So the series is organized by 3 folks. It's organized by Andrea Volkhammer, working at Charité, Andreas Bender at Terra Lumina and at Cambridge University, and myself. And before we start with today's event, I'd already like to take your attention to the next event. So we decided we'll still have one further edition before the big summer break, and we are currently planning for end of June, June 30. And as you have seen, this meeting is being recorded to make presentations available afterwards, but of course the socializing part will not be recorded. If you have any questions, please feel free to put your questions into the chat window while the presenters are presenting. But then at the end, we will go through the questions orally. So if you have the option to unmute yourself, you can verbalize your question yourself. Exactly, and please stay on afterwards if you can. And if you wish to present, or if you would like to present in the series, just let us know. And we always put together new editions of this. So with that, let's come to today's edition. I'm very happy that we'll have a topic which is very dear to my heart, as some of you might know. It's about free energy calculations. We'll have 2 talks on free energy calculations by Tony and Christina. And Tony will start, and I'm happy to introduce her. She's a Chancellor's Fellow at the University of Edinburgh, which I find is a very nice job description. And Tony told me that this is an assistant professor tenure track. So congratulations to that. Prior to this position, she did a postdoc with Julien Michel in Edinburgh and a postdoc with Frank Noe in Berlin. And she holds a PhD in physics from the University of Nottingham and a BS in physics with chemistry from the University of Kiel. Is that correct? She's nodding. And Tony loves and promotes math and is very active in an organization, a non-profit organization called Imaginary, that you might want to look up if you're interested in promoting math. And she is also a consultant to Extensia. And what some of you might not know, this is a Berlin seminar series, right? Tony grew up in Berlin and I guess loves the city still. And today she's going to talk to us about everything you wanted to know about alchemical free energy calculations, but were afraid to ask. And with that, Tony, I will stop sharing. And the floor is yours.
All right, can everyone hear me and see the slides?
I can see you, I can see your slides, I can hear you well.
Wonderful. Well, then thank you so much for the wonderful introduction. And thank you so much for giving me the opportunity to speak here and present a little introduction to alchemical free energy calculations. And I'll keep this very much on the sort of what is the method side, and then hopefully Christina, or I believe Christina, will talk more about the applications. So if you're itching to know about applications, you'll have to wait until the next talk. So alchemical free energy calculations, well, no, not quite the free energy calculations, but alchemical processes and recipes have been around since the 15th century. We don't quite try and make gold anymore, but funnily enough, the 2 recent publications I'm mostly going to talk about, which kind of describe the best practices for these alchemical free energy calculations and for how we can actually define a good data set to run them, kind of resonated quite well with me, that this is similar to this 15th century publication. But kind of to get a little bit started, I guess I don't need to convince you as an audience that it's important to optimize certain aspects in small molecule drug discovery. So we want to have a good binding affinity, selectivity, low toxicity, high potency, and all that. And a lot of these things are nowadays estimated using computational techniques to speed up this early stage of drug discovery before we can go into the preclinical trials and clinical trials. And in particular, what I would like to highlight today is computing binding affinities, and particularly computing these using a tool called Alchemical free energy calculations. And this tool is based on molecular dynamics. So before we even go into the alchemical free energy calculations, I kind of want to motivate why we need to do this kind of very complex way of doing it rather than just using standard molecular dynamics. So what is molecular dynamics? Well, you hopefully are familiar with what a crystal structure looks like. Here on the left is a crystal structure of a metallobeta-lactamase. You've got a ligand bound. I've kind of highlighted the binding site residues. Don't worry, we don't need to understand what's really happening here, but it gives you a very static image. A simulation, however, kind of gives you a much more moving image. It creates a movie of what is happening. So you have your drug molecule trying to explore different conformations until it eventually finds a good binding site. And this is the kind of thing we want to explore in alchemical free energy calculations. So they're really used to create movies, but rather than just looking at the movies, we want to actually make quantitative predictions from them. And we also get some kind of atomistic resolution from these simulations, so we can understand if you have a binding site, conformational change, and so forth. So how do we actually create this movie? Well, we usually start out with a crystal structure. Then we solvate it, so we add water and ions to create a environment that resembles that of our in vivo environment the best we can, or at least our experimental environment. So maybe the in vitro experiment was different. And then usually what we need to do is find a way to describe how the atoms will move. And for this, rather than using quantum mechanics, which is super complicated to solve, we actually approximate everything using Newtonian mechanics. So we define a potential function, also called force field, that basically models how our bonds vibrate, the angles move, torsions, how van der Waals interactions occur, how charging interactions occur. And by defining this potential, which is just the sum over all the potential interactions within our system we're trying to simulate, we can take a derivative of that gives us the forces. And then if you think of your hopefully high school physics, Newton, F equals ma, that gives you information about the movement in your system. You do have to do a little bit more work. So you also want to probably minimize the position so you don't get something blowing up. You probably want to equilibrate your system, but eventually you get to the point where you can actually run a simulation and query it. So how do we get to binding free energy from that? So if you think of the concentrations of your ligand and your receptor, and eventually if they are binders, they will form a complex, and you can look at what your on rate and your off rate of these is. And if you look at the ratio of these on-off rates, and therefore also the ratio of these concentrations, that gives you the equilibrium constant. And the equilibrium constant is related to a free energy. I mean, often in experiments, you might be able to measure a KD, but typically in my field, I guess we're more interested in this delta G, so the free energy of binding, and you get that out of the equilibrium constant by taking minus the log of the Boltzmann constant times your temperature, and then the log of this K on and K off rate. So from our simulation, what we might want to know is, what is my K on and K off? So we just need to run the simulation often enough for this ligand to bind and unbind the protein. And this is kind of where the problem arises. So a typical drug off rate is, I don't know, 10 to the minus 4, let's say, per second. Typically, we can simulate, depending on the size of the system, say 300 to 600 nanoseconds per day. Maybe we can even push it a bit further, but that's kind of the maximum what a GPU at the moment, or a good GPU computer, would allow. Well, actually, we're talking about maybe a HPC at this point, like a cluster of computers. But really, in order to get good statistics, we want something like 3.6 times 10 to the 12 nanoseconds to get this 1 hour long simulation. So you get enough events of unbinding and binding. And then suddenly we're at 3 million years to complete this simulation. And so that becomes unfeasible. We need to find a different way of actually estimating this binding affinity, but we still kind of want to use these MD tools because they actually tell us something about the movement of the protein and the ligand. So what can we do? Well, this is the problem we have. We want to know what the free energy of binding is of a ligand 1 to some kind of protein. Often we're actually interested in the difference between the binding of 2 ligands, though we're not necessarily interested in just one. So we want to be able to tell if ligand 1 or ligand 2 binds better. So actually we have twice the problem, but that is something we can use to our advantage because free energy is a state function. So actually we can write down this thermodynamic cycle where we say, well, what if we move our ligand 1 to our ligand 2, as in we kind of alchemically perturb it, and I explain a little bit more how we do that in a moment. We can actually estimate this free energy difference between these 2 ligands by calculating the legs that here are shown in green in this thermodynamic cycle. So we're actually trying to morph our ligand 1 to our ligand 2 while bound to the protein and moving around freely in water. And that is equivalent to that really, really long simulation. And in fact, we can run these at a much shorter order, timescale order. So typically 2 to 3 hours on a modern GPU or on a set of modern GPUs is now possible. And how do we actually run the simulation? So what we define is a set of alchemical intermediate states. Usually we use a lambda parameter that kind of switches between them. So at lambda 0, we are fully interacting one molecule, and at lambda 1, we are this other molecule. And let's explain this a little bit further in detail. So how do we actually define how we do the morphing? So typically we would define what is the maximum common substructure of our 2 molecules. So in this case, this is the benzene ring here, and we just have this methyl group that gets added. So in the morphing process, we will take this hydrogen and slowly turn it into a carbon that then has all of these extra groups attached to it. And we do this through a switching function. And the switching function describes our standard system, which are the coordinates q, and then has this extra lambda parameter. And depending on whether lambda is 1 or 0, you're in one state of the molecule or the other state of the molecule. And anywhere in between, you are sort of halfway between molecule effectively. And in order to do this in your computer, you typically use something called a soft core potential. So you're basically softening the way your force field interacts. And then how would you actually practically run this kind of simulation? So you have different options. The most simple one you can think of is by just running replicas at these different lambda values. So if you start at lambda 0, then have 10 replicas all the way to lambda 1. And actually finding the right number of these windows can be quite tricky. You don't want to run too much, but not too little. But that is for a different talk. You could also do something like a replica exchange, where you mix the replicas that hopefully promotes better statistics. Then there's other approaches that use non-equilibrium switching, where you would start where you just have a long equilibrium runs at each endpoint, so each of the 2 molecules, and then you use a non-equilibrium switching method to go between them to estimate the work that requires. And then quite recently, there was a paper by the Assure Research that introduced time square sampling, where you effectively just have a single replica exploring this space. So we've run these simulations. So we've done my simulation in water. We've done my simulation with these different lambda windows while connected to the protein. What we're interested in is this delta delta G. So how do we get this delta G out in the first place? So here's a plot of the potential mean force estimated with two sort of common estimators for estimating free energy. So these estimators are important to actually get your free energy out. And probably, well, I think historically, maybe they've been around similar sort of time. So the first one is thermodynamic integration, which basically at each point of your lambda simulation, you take a derivative of your potential with respect to lambda, and then you average it. And then you can integrate over these average points, and that gets you a free energy. And there's a lovely derivation you can look at that actually shows that this is true. And then the other one, which looks a bit scary, and don't worry, I'm not going to explain it in great detail, is multi-state Bennett's acceptance ratio, which you may have heard of the 20 equation or the Bennett's acceptance ratio. This is effectively an extension that takes in more information and falls into a class of so-called reweighting estimators. And the way they work is effectively that you have a set of two equations that you need to iterate into convergence. And what you're iterating for is this FK hat, which is the free energy you're trying to estimate. Okay, so far what we've done is compute the free energy of one set of ligands. Typically, we're interested in more than one set of ligands. We actually want to simulate 20, 30, 50, 100, maybe even 1,000. So we need to find a way to connect all of these ligands to get these relative free energies. And what we do is build up this perturbation map to do so. And here, I guess, you are limited to the fact that you want these ligands to be fairly similar. So you do have some kind of maximum common substructure for overlap. But once you've defined your map, you can then run all these edges. Then you analyze them with your favorite estimator. And then you can actually compare your experimental values to your calculated values. And then you kind of hope that they all fall on this x equal y line. So here's an example of tyrosine kinase 2. You have 34 ligands, and these are the edges I'm plotting. So there's different ways of plotting it. You sometimes want to look at the delta G's and not actually the delta G's. I chose here to illustrate the delta G's, and you get a mean unsigned error of 0.79 kcal per mole and 1.1 for your root mean square error. So the next question is, how do I actually simulate them? Well, there's lots of different ways to do that. There's a bunch of commercial tools by Cresset, Schrödinger, OpenEye, and other folks. There's a bunch of academic tools such as GROMACS, Amber. By SimSpace is a tool I've built that kind of lies on top of Amber and GROMACS and Cyrmol, and as a Python framework to do these free energy calculations. And then more recently, there's this Open Free Energy Consortium, I think Christina will mention, hopefully in a bit more detail, that is trying to kind of unite and build something for the drug discovery industry. So this kind of gets me to conclude the first part of my talk. We've kind of established a bunch of best practices for running alchemical calculations to make them robust and reproducible. If you are interested in more details, there's this publication from 2020. It's only about 50 pages, so a super easy read. Yeah, but how do we actually then go about in evaluating, say, a new tool or a new force field? So what we really need is also a standardized way of defining our benchmarking for the data sets we want to use. So in this 2020 paper, we already highlight a bunch of data sets. And in particular, I want to draw your attention to this FEP plus data set, what we call FEP plus. Effectively is from a paper from 2015 in JAX that looked at mostly 8 protein targets. So go from thrombin to base, and you have a bunch of kinases in there. And this is something people have used over and over and over again. So we used it for FLAIR. Then AMBER people have used it. GROMACS people have used it. But you've not necessarily used exactly the same data. You've maybe used the same X-ray structures, but how do we know that we actually have a standardized data set that is good? And this is kind of what we've been asking in this publication here. So just because we have crystal structures, are they any good? Can we actually pre-select a good set of structures where we all agree that they're good? So here, for example, in base hunt, you might have electron densities for 2 side chain conformations, but this one seems to have a much better interaction with the ligand here. So you probably would prefer that for your simulation than another one, or a different situation where you have we have 2 structures of spleen, tyrosine kinase in this case that have very little density around the ligand and the active site side chains, and the second structure that does have a lot of electron density. So really you want to use this structure. So can we find a way to actually assess whether our structures are any good? So thankfully, Warren et al. Kind of looked into this in 2012 already, and this is something we now promote with this best practices paper, is to use the Iridium score for figuring out whether a protein structure is good or bad, effectively. So it takes in 12 features, amongst others, resolution, density of coverage of your ligands, and so forth. And then you can classify your active site and your ligand into a highly trustworthy, a medium trustworthy, and a not trustworthy structure. And surprise, surprise, you probably want to simulate highly trustworthy structures. So if we go back to this FEP plus data set, how good are the structures? So the ones used are mostly fine. I think there's one of the junk kinase that is actually not very good at all. And then there's a bunch that are medium trustworthy, but the PDB does have good structures. So maybe we should actually use a highly trustworthy structure in our data set rather than the original structure would run, just because that's what has been done. And then you can also look at ligand data. So do you want a ligand? How do you want your ligand data set to look like? So you probably want more than, say, 8 ligands in your data set. You probably want a large dynamic range in order to actually test your methods well, because yeah, otherwise you might run into problems, because typically people tend to say, oh yeah, general accuracy you can get is about 1 kcal per mole, root mean square error, correlation coefficient of 0.8, Kendall tau of 0.8. How realistic is that? Is that a good statement? I mean, that's kind of what we saw from the plot earlier I showed, but actually Christina Schindler did this really great way of estimating how good can your model actually be based on your experimental data you have. So here we're basically modeling experimental data with different Gaussian errors. So we have a sigma of 0.5, 1, and 1.5, and you can see that if your error in your experimental data is quite large, then suddenly you can't really expect a very good Kendall tau correlation or root mean square error. So this might not necessarily be true for your data set. So you kind of need to think about how this relates to your data set. And then obviously there's efforts to improve accuracy through machine learning. So there's been multiple studies that try and take information from the free energy calculation and then figure out what is actually the better free energy calculation. So this is something we did where we learned the offsets of the free energies. There was work done by John Codera that replaces the ligand force field with a machine learned potential force field such as Annie, and suddenly these values become better, but you still have this upper cap of how good it can be based on your experimental data. Okay, so now we have a tool. We have best practices for running free energy calculations, and we have a best practices benchmark data set. So now we're really in the position to actually do some robust testing of what happens if we try and improve our force field, or if we play around with how we define the perturbation map. What happens if we use different simulation engines, or even what if we don't use MD and try and use a neural network and instead. So I've talked about many things that work. I didn't talk about some things we can do. So you can also look at protein mutations. You could look at partition coefficients, membrane insertions. You can run absolute free energy calculations in a situation where you have very different types of molecules. So these relative perturbations don't work. But you might also run into issues. So charge changes can still be a challenge if you try and do scaffold hopping or ring breaking. These things do work in some codes, but not in all. Then my PhD student, my bachelor student, soon to be PhD student, Ryan, had a fun problem where he realized halfway through all of the simulations that actually he needed to use a constant pH simulation, because the pKa of the molecules was such that they should be protonated / unprotonated. You might have problems with systems with cofactors or metals. So these are kind of issues you might want to be aware of. But hopefully I've convinced you that having best practices for running these calculations and having best practices for benchmarking really now provides an opportunity to rigorously improve affinity predictions and creating new methods that can be tested in a sensible way. And with that, I would like to thank you for your attention. I will point out my group, although apart from Jenke, none of them had been around, because I started in 2020 in the beginning of the pandemic. So a lot of this work was already on the way. And yeah, thanks. That's it for me.
Thank you very much, Tony. So feel free to put your questions into the chat. You can, I think that's the easiest so far. Let me start with a question. Tony, you have now sort of like really through this best practice work, you have really dig deep into what people are actually doing, what works, what doesn't work. So from the experience you have gained now, where should we focus, in your view, our methodological development efforts? So what's the biggest problem?
So, well, from a personal perspective, I think for me, the most interesting ones are making constant pH simulations kind of standard available in these tools. I mean, methodology kind of exists, but there's no easy way to actually run them. And then I guess that is kind of my main research, is how can we do things with metalloproteins. I guess those are my personal favorites. And then I guess making these tools work for standard problems such as selectivity would be good, that you have a recipe where you can just kind of, here's a way to assess selectivity in a sensible way, is something I've been asked about a bunch. So clearly this is something people worry about. Oh wow, there's lots of questions on me.
Okay, let's start with the first one. Yeah, sorry, Antonia, you were. I didn't want to interrupt you.
No. I think I was about to ramble on, so let's go to some questions.
No, I couldn't complete. I mean, the constant pH is also in practice, I think, something that we really would love to have. So, question from Jonathan. Jonathan, would you like to verbalize your question and unmute yourself?
Sure, thanks. Nice talk. So you mentioned, I guess, a growing use of machine learning potentials. So I was just wondering how off the shelf they are. Could you run through a library of 1 million ligands in some virtual screening and be confident that the parameters were good, or do you have to be a little bit more cautious than that?
So, I mean, I don't actually know whether they're routinely used in virtual screens. So I know that OpenMM now routinely does support multiple machine learning potentials, and but I don't think anyone's actually tried to run alchemical free energy calculations purely with machine learning potentials. This is something people are working on, or at least maybe people have done it, but I've not seen it published anywhere. So yeah, there's software frameworks that do support them. I guess one of the things you kind of need to be wary about is making sure that you know exactly what you're running effectively, because I think you need to be very careful with documenting your experiments there. I think using different force fields is already kind of a fun problem, and now you're just opening Pandora's box a bit more. But I think they're very exciting and really promising. So yeah, definitely something to consider.
Okay, thanks.
Tomasz is next. Tomasz, can you unmute yourself and verbalize your question?
Yes, sorry, it was a little bit technical. No, yes, so I actually have a very basic question, but maybe it's complicated. So I was curious, do you have any thoughts about, or what, according to you, would be the best practice in respect to halogen atoms and halogen bonds? So you know that force fields kind of differ in how they treat them. And I'm just very curious, from your experience, what would you recommend in this kind of calculations?
Yeah, so surprisingly, well, or unsurprisingly, halogens can be not very good at capturing free energy. So you'd think that if you just change a chlorine or something, not chlorine, so yeah, chlorine. That is a halogen, right? Am I?
Yes.
Yes. Okay. Sorry, it's too early. You can run into some problems. For sure, we've seen that where you kind of just move a chlorine about, and you'd think that should be an easy thing to do, but it's not necessarily. I've not really dug into the force field development there. I think, again, I'm kind of hopeful that these machine learned potentials will help with it, rather than trying to solve it in a sort of classical force field way. That we might take.
I mean, Tony, maybe to add on from a practitioner's point of view, so we have quite good experiences with this sort of like bug fix kind of way with an off-center positive virtual charge. So that in practice works quite well, in my opinion.
Cool. I didn't know that.
Yeah. So next question from Surahit. You want to verbalize your question? So maybe I read it. It's how far do you think we are in terms of protein structure prediction with changing pH? FEP Plus and NAMD offer this functionality, and I'd like to know your evaluation of it.
I mean, I don't know anything about structure prediction. This is not.
Okay.
I don't think I can.
So this is a question for the socializing event. So anybody who knows this can.
Yeah.
Christian, you're next.
Yes, thanks for your talk. So I was wondering if you have actually studied the impact of the structure quality in FEP outcome predictions. So what is the RMSE actually it would help to solve, or how good is it when you use the better structures? Because you would assume if you run an MD, you might cover that.
Absolutely. So we've not done this systematically yet. I think what we're trying to do at the moment is effectively run the benchmarking data set, but using alpha fault structures as a sort of first comparison of here's a crystal structure and here's a machine learned structure. I've definitely had experiences around if you accidentally leave out structural waters, that things get really bad. Certainly if you use a wrong sidechain orientation, getting that to flip cannot happen, so that will give you bad.
You also thought you have, I mean, the data set, and then you look for better structures. You could just rerun this and see if you improve the army.
Absolutely, yeah, this is definitely something.
Yeah. And with AlphaFold, I think what is also said, it's very good in APO structures. But I mean, if you have some small changes in the sidechains, AlphaFold normally doesn't get this. So it would be not a complete fair comparison actually to use AlphaFold structures.
Probably not, but it's an interesting experiment, because I guess people are very keen to use AlphaFold structures. So we want to know what can we expect from them, I suppose.
Okay, thanks.
Okay, let's take a couple of more questions before we go to Christina. So Damish is next.
Hi, thank you. It was nice talk. So I have a question regarding the better force field for alchemical calculations. I was wondering, have you explored or used BMX force field developed by Bert de Groot from Max Planck? They said their accuracy is higher, like compared to experimental data. Yeah.
So I guess, well, I'm aware of this development. I have not personally used it. This would be a perfect thing to try with the benchmarking dataset. I think they actually did show this using this benchmarking dataset, but set up in their way effectively, rather than the way that is standardized, or we're hoping to standardize. So I can't comment other than, yes, that is what I've seen, but I've not, we've not run it as a standard set against the way we do things effectively. So the publication they've published on this looks good. So that's what I can say.
Yeah, no problem. Thank you.
Thanks, Tony. I think in the interest in the time we move on, but there's still many questions left in the chat, so maybe you have a chance to answer some of them, or otherwise if we stay on for the socializing part. And with that, I'd like to thank you again for this great overview and introduction, and we move on to Christina. So happy to introduce her. So Christina is a principal scientist at Merck in the meantime, and she holds a PhD from the Technical University of Munich and a master in physics from the University of Heidelberg. And besides her work at Merck, she is on the governing board of the Open Free Energy Fund, and I guess she will also tell us a bit about this. And today she's going to talk to us about applications and impact of binding free energy calculations in drug discovery. Christina, I'm very much looking forward to your talk.
Yeah, thanks, Clara, for the nice introduction and the invitation to this. And as it was already announced, I will now try to cover a bit more the application sides on binding free energy calculations and the industrial perspective of how we use this technique in drug discovery and how we think it adds value to our projects and in what way we need to use it, that it can give such value. First of all, I want to first I want to acknowledge my colleagues who contributed to this work, especially Daniel Kuhn, Christine Rakas, and Andreas Evers, who contributed some of the application cases that I will show later today. And also our colleagues from Schrödinger, who are constantly supporting us in this work today. I will only show results which were generated with the FEP plus method from Schrödinger. And then later I will also briefly touch, as already announced, on the Open Free Energy Initiative and the Open Free Energy Fund. So yeah, in our company, we also got, as many others, very interested in binding free energy calculations in the first half of the last decade. And around 2016, we started a very large initiative to try out this technology or the implementation of binding free energies by Schrödinger, FEP+, in our own drug discovery projects, and really try to evaluate broadly how good it is under real life conditions. And this was also the start of my career at Merck. I joined as a postdoc with exactly this task, to take this method and bring it into as many projects as possible and many different protein targets, and look how good it performs in all these different targets, and also under the real life time pressures and the knowledge gaps that we have in our ongoing active projects. So for this, in total, we looked at 28 different protein targets at that time across our whole portfolio of targets and projects, and evaluated whether in principle it would be feasible to do FEP on these. And for a certain number, it was not feasible because no structural information was available. And then for those where we had structural information and also a certain set of ligand data available, we tried to run an initial retrospective study, what we call the initial validation study. From this, we obtained 14 of these different protein targets where we got this initial, that they passed this initial validation, where we thought, okay, their FEP seems to work for this target, at least to a certain degree. And then we moved this forward and tried to also use it actively in the project, really predict compounds of FEP and then have them synthesized and tested and compare how good are the predictions against these newly synthesized compounds. In total, we ran this across 3 years and covered 35,000. We performed 35,000 of these single edge calculations that Antonia explained so nicely to you. And in the end, we collected a data set of over 6,000 final predicted compounds, and roughly over 400 of these were eventually made and tested. And so we were able to compare how well FEP performed under this real world settings, and also what are the learnings from using it, and what is actually the impact of this on projects. And in 2020, we also were finally able to write this all up and have a publication. And I will not go into all the details of this quite long paper, but I will highlight a few of our key learnings before I then later turn to our new applications or current applications of FEP in projects. So as I said, I'm not going to tell you everything that is in that paper, but I want to highlight 3 main learnings from this. And the first one for us was really that the accuracy we see for FEP can really vary very broadly between the different protein targets. But maybe what was more even surprising for us was that it also varied within one given protein target. It varied between the different chemical series that we looked at. So having one chemical series where FEP seemed to work nicely was no guarantee that it would work also equally nicely, predict equally well for another series for this given target protein. And an illustration of that can be seen here in this first graph, where we have plotted all the results of the root mean square error we observed in our initial validation studies for the different chemical series. And if you look at this yellow protein, you can see that we got very high accuracy predictions in one chemical series, but also rather lower accuracy predictions in another one. So here it really seemed to was varying from one series to the other. Also, we then collected the prospective data sets. So those that where we really first predicted the compounds and then they were synthesized after. And for this, we collected these for 12 different targets and 19 chemical series. And overall, these results tended to be of lower accuracy than what we generally see in benchmark sets across method development papers. Generally, we also observed that these were lower than what we were seeing in our initial retrospective validation study. There's a lot of reasons why what could contribute to this, but of course, it's also tied to the uncertainty and also the general challenges of using FEP in projects is that you never have such an ideal situation. Usually you have uncertainties, maybe about the ligand binding mode. You have maybe not an ideal structure, as we've heard before. It's of course, very good to have a really highly resolved structure, but when you work on a project, you have to make do with whatever is there. And all these things can really contribute to that we are not seeing maybe as good accuracy during the active project, as we are seeing later than when we really synthesize the compounds. And this has taught us also that it's very crucial to monitor the accuracy throughout the project. The second thing we have learned from this is really that benchmarking actually itself is not as very challenging task, and it's actually that we also realize that the setting of prospective benchmarking is maybe the most challenging, because you have no control over the data set that you are evaluating. And then coming back to what Tony showed earlier, it is very hard then to draw robust conclusions from these data sets. And this has actually also given me a lot of learnings. And based on this, I've also collected larger retrospective data sets that we've also presented in these publications, and that have also entered the best practice data set paper that you saw previously. The third learning we had is that even when we get really nice accuracy, when we are really able to predict the binding affinity of compounds well, that this does not equal impact on projects yet. And I will go a bit more into detail what I mean about that. With impact on projects, I mean, are we able to help the project move along faster? Are we able to influence our projects in such a way to decide which compounds are really worth making? And in principle, of course, FEP is a really great method for that, because if it can predict the binding affinity to high accuracy, then of course it can help us to say this compound will be a good binder and this compound will not be a good binder. And maybe the ones that Jen predicted not to be good binders are the ones we shouldn't be making. So high accuracy and also staying within the domain of applicability is something we always need to be aware of in the projects, but it's not the only thing that we need to have really success when we use free energy calculations in our drug discovery projects. The second pillar is really timing and communication. We need to make sure that everyone in the projects understands the limitations, the domain of applicability of the method, and also that we deliver these results in the right time. If the calculations take weeks, and if chemists have in between already decided to synthesize the compound anyway, we will not influence the projects in any way. So really also having good throughput and executing on this is really important. And also timing also refers to the timing within the project. If we noticed actually that for us, using free energy calculations in the earlier stages of the project, when the synthesis was not as well established, was often perceived as more valuable because the chemists were struggling with the synthesis. It would take them long times to synthesize some compounds, and then they were more happy to receive suggestions which of these compounds should be made or not. And in contrast to later stages in the projects where synthesis probably moves fast and some modifications are just easy to make and no one wants to wait for calculations to complete. Rather, the compounds will just be synthesized anyway. And this also brings me back to the third pillar that we have to balance when we really want to use free energy calculations successfully in projects. And this is about throughput on the one hand side. We need to be able to evaluate large number of compounds, prioritize large number of compounds in a short cycle time, such that we can keep up with the design, make, test cycle in the projects, and also always are up to speed to the new data that come in the project. And also, of course, if the costs for such calculations are too high compared to the cost of synthesizing the compounds, this, of course, also doesn't add as much value as we would like to add to the project. And from this, we have identified a couple of use cases where we think that this really helps to balance these three pillars and really ensures that our predictions also make an impact on the project. So on the first part, of course, it is always good that we can help to focus from a large number of ideas towards a few number and really prioritize these large number of ideas for synthesis. But the focus here is really on the large number. So there's no value in prioritizing 8 out of 10 compounds for synthesis. It just takes too long with FEP. I mean, then the chemists could just make it themselves. Rather, I'm talking about prioritizing from 100 to 10 ideas. The second use case we've identified is really this idea of covering chemical space more broadly. So when we evaluate molecules in silico, you can of course consider all kinds of chemical modifications, and in this way we can increase the structural diversity in a project and explore the chemical space more broadly with designing and enumerating libraries, and in a way that couldn't be probably done under the normal budget constraints of synthesis in a project. And this kind of enumeration is also one of the most used enumerating a library, mostly based on building blocks, and then prioritizing these large libraries from a couple of thousand molecules to like 20 molecules that we will synthesize is one of the most largely used cases in our projects. And the third case we see as very valuable is when we have really challenging synthesis, especially, for example, when the central scaffold is changed, even by one atom. This can require a whole new path of synthesis, and to de-risk such changes in the scaffold, and especially in the early projects where you usually often might have to change the whole synthesis there, it can really provide a lot of value to use FEP to support the design of the new compounds. So now I will share a few of our recent applications. And one of the first applications I want to highlight is applying FEP in the design of PROTACs or heterobifunctional degraders. I think maybe some of you have heard about these. So this is a new class of drugs where instead of inhibiting a protein, the protein is actually degraded via the internal ubiquitin proteasomal pathway. So it is really removed entirely from the cell. And for this, one way to do this is to have these PROTACs that have two binders, one binder to the target protein, one binder to an E3 ligase, and a linker in between. And these molecules are very big and very challenging, and they have these three regions and a lot of things to optimize. So here it's really also very good if you have a method that you can support this optimization and cut down this large space of different things you could change on this molecule and prioritize. And this is also what we use FEP for our degrader design for. So here's an example from the project. So initially we had a binder that had a binding affinity to the target of 22 nanomolar, and it had 3 hydrogen bond donors. However, and we made a PROTAC out of this, which was weakly active with and degraded the protein with a DC50 of 27 micromolar. And the resulting PROTAC from this binder had then 5 hydrogen bond donors, which was something that we didn't want. We wanted to reduce the number of hydrogen bond donors for this. So then we evaluated different binders with FEP, and the idea was to reduce the number of hydrogen bond donors, but also maintain the potency. And one of these binders was actually predicted to bind with even stronger affinity and also had a reduction of 1 hydrogen bond donor. And what was even nicer was that this was also not covered by our previous patent and would provide even new IP for us. And then we made the PROTAC from this with exactly the same linker and the same E3 ligase binder as the PROTAC 1. And actually this one even showed also an improved DC50 and had, translating from the reduce in hydrogen bond donor in the binder, also had 1 hydrogen bond donor less. And currently in the project, we are now looking at reducing the hydrogen bond donors even further for the binder. And also the idea was to reduce also 1 aromatic ring from this. And for this, we are applying such a library approach where we generate new ideas using an AI generative model. And then these compounds will be docked and evaluated with FEP. And from this, we will then select our molecules for synthesis. And these then have to be always translated again in the PROTAC. And so you cannot explore too many binders and have to be a bit selective about the binder itself. Yeah, a second project comes from my colleague Daniel Kuhn, who was in a project where they had a backup class and they wanted to optimize the potency of this backup class. At the moment when they started the project, the best compound in the class was, I think, 800 nanomolar active. And of course, they wanted to improve that even further. The initial synthesis was focused on one particular part of the molecule, and from just normal idea generation, the team had already evaluated 200 compounds with FEP. However, none of these were predicted to be more active, and they had already also synthesized like 30 compounds, and also these didn't improve potency. And at that time, we thought, okay, can we maybe do something more? And this was our case that we wanted to look at whether we could also screen a larger library. And in this case, this compound was actually a part of the enamine, or had very similar neighbors in the enamine real space. And from this, we pulled 35,000 compounds that had the same core and this variable R group in this one position. And in addition, we also did a reaction-based enumeration in this part and used a chemical language model. And we had a large number of compounds, and they were too large for FEP, but we still wanted to evaluate all these compounds and see if any of these would be any good for to try for synthesis or for purchasing via enamine real space. And to deal with that, we then combined FEP with a machine learning approach, where we do use an active learning strategy. We initially selected 500 compounds that were evaluated by FEP, were docked and then evaluated by FEP. And then from this, we built a machine learning model to evaluate the whole set of compounds. And from this, we then prioritize the best 500, and we again evaluated these with FEP. We built an improved machine learning model, and we ran through this cycle 6 times. So in total, we ran FEP calculations on 3,000 compounds to evaluate this whole large library. But unfortunately, from all these efforts, only 10 compounds were predicted to be in the similar range as the reference. We went ahead, we purchased 12 of these compounds, so we added two of these that were a bit even of less potency, and out of these 12, 6 were active. However, none of them, the best ones showed a similar affinity as the reference compound. And this then led the team to conclude that varying the molecule in this particular R group had not really any benefit. And then the synthesis was actually refocused to another part of the molecule. And indeed that helped, and then in the end brought an increase in potency. And I think in this way, FEP actually helped to, by this broad coverage of chemical space, it gave the team really the confidence that they could move on to another part of the molecule. And this actually then also helped to move the project forward. So yeah, in the last 2 cases, I will come to some new developments, that always come up, and that also relate a bit to the method development that is always needed. Then whenever we move to a new protein target class, as is the case here in the project of my colleague Christina, you always face new challenges. And Christine actually had a project that was structurally enabled, where we had nice crystal structures, but unfortunately the ligand, or not unfortunately, the ligand is binding to the protein, and this binding is mediated by metal binding. So the metals are really, really important in this binding site. And when Christine initially ran FEP, with just an FEP class with just the default settings, you can see this result on the left side here. That didn't look well, and she was not satisfied with that. And one of the reasons for that was that really this metal coordination with the ligand that we observed in the crystal structure was not well preserved also through the simulation. And then she contacted our colleagues at Schrödinger, and they put in a lot of effort to study the system. And also they tried out a new protocol they have already developed internally for FEP plus for metalloproteins, where a 0 order bond to this metal is considered, and also tried different conditions like salt conditions and so on. And in the end, indeed, they were able to come up with settings that you see here on the right, which show much improved accuracy. And this is now something we are taking forward in the project to support it. But it really shows that also this continuous method development is really necessary, because whenever you start to use this more broadly for more protein targets, you will eventually encounter something that doesn't work well and that requires further optimization. So last but not least, we are also recently moving towards applying FEP more in our antibody-based projects. So this is an example from my colleague Andreas in a project where they obtained a crystal structure of the target binding to our internal antibody hit. And he first designed over 1,000 variants, varying all the amino acids in the interface, used the Schrödinger residue scanning tool, and then reduced this to 50 variants. And these then went into a protein mutation FEP. And they were also evaluated by additional machine learning developability scores we have in-house. And yeah, currently he selected up to 10 variants that will be processed, and hopefully we will also see the results of that soon. And depending on how that looks, this is also, I think, a very promising application for the free energy calculations in our company. Yeah, last but not least, I want to switch gears towards the Open Free Energy Consortium. So this was also already mentioned, but as you've seen, we are really looking towards applying FEP on large scales. And so the software itself needs to be robust, but also ideally we would like to run it on as many cores and resources as we have available, and not be limited by any licenses or anything. And we are very excited that it was possible to bring together a lot of partners from industry. Currently, we have 14 industry partners in this consortium that support creating an ecosystem of tools for free energy calculations that are open source, interoperable, robust, automated, scalable, modular, and extensible. And I think all of these parts will be very important to help us get really to an open source protocol that we can run on as large resources as we like, to really put free energy calculations in projects then to the next level. And yeah, if you're interested in this consortium, feel free to reach out to me. And of course, it's also always possible to join if you would be interested in that. And with this, I'm coming to the end. Can proudly say that across my postdoc and also my time as a scientist now, FEP has been really established as an expert tool in our computational chemistry toolbox at Merck. So actually now all of the computational chemists in our group have used it in their projects at one time or another. But we are currently really, we've learned really that we need to focus it on high impact applications, and we have, I think to my knowledge, identified the cases where this makes most sense. What we see as most promising is really this combination with ML, that we get the speed up and to really be able to move to screening even larger libraries, also for absolute binding free energy calculation, that we combine this with active learning. And in terms of the software developing, we are very happy that we are supporting the Open Free Energy Initiative, and we hope to see that this will also deliver like new open source tools for free energy calculations that everyone can use. Yeah, and with this, I'm at the end of my talk, and I'm looking forward to your questions.
Thanks, Christina. Thanks for this insight also in your recent application scenarios and use cases. There are really lots of questions. First is from Andrew. Andrew, would you like to verbalize your question?
Sure. It was more of an observation and a speculation. I noticed in a lot of these graphs showing FEP against calculated energies against real binding energies, and some in the some graphs that Antonia showed as well, it seemed as if there were more molecules which are sort of on the negatively skewed side. That is, they have lower FEP PK than they do real PK. And I wondered if that was actually quantitatively the case, and if so, if you had any speculation as to why.
So you're wondering if there's a systematic deviation between, so either compounds are systematically over predicted or systematically under predicted. Is that your question?
Yes, that's the question.
So yeah, maybe unfortunately it was a bit different between our two talks, but on my side, the experimental data were on the x-axis and the predicted on the y-axis. And this brings me that we more often observed that that we had compounds that were predicted to be really good and they were not that good. Most of the time I had rather the observation that if it was predicted to not be good, it was also never good. But I mean, this might also be a bit a selection bias. Yeah. We always wanted to synthesize those molecules that were predicted to be highly active. And I mean, for the ones that are predicted to be not so active, we usually don't synthesize many of these.
Yes, of course, that is the issue there. Thank you. I think that, yeah, makes sense.
Christian.
Yes, thanks a lot. So we have also seen a kind of, I don't know if it's behavior, but whatever of FEP that you cannot sometimes predict between series, even if they're well resolved, you know, the binding mode and so on. What is your experience in gaining understanding why that is? And in my experience, it's more like a black box. So we always tried some things, but we never could get anywhere there. But maybe you have a bit more insight in that. So I'm interested in that.
Yeah, that's also something that I've really wondered about, how it can be that it can be so different between chemical series. And unfortunately, I also don't have an answer to that. Sometimes we wondered if some of these series might have an effect on the assayer or that was something where this was coming from. But so in terms of looking at the solubility or something like that, but we never figured anything out.
Okay, thanks.
So next question is from Ernest. I will read this one. Did you compare charged versus uncharged ligands and how do the results compare? Also, did you only use FEP plus or other codes like Romex, Amber?
So yeah, we did compare, for example, charged versus uncharged ligands on this retrospective data sets and also published, and there actually the errors for charged perturbations were larger than for uncharged perturbations. What was the second part of the question?
Whether you had used other codes than FEP plus like Gromex or Amber.
We've not used Gromex or Amber internally for free energy calculations. We evaluated also Flare version 3 at some point, and for some of these data sets, this also gave very good results, but mainly we use FEP plus.
Thanks, Christina. Next question is from Tobias. Do you want to verbalize your question?
Yeah, sure. Thank you for the great talk. I was wondering if you have any learnings regarding interactions with saucer. So, for example, you know, the sigma hole in a thiophene, or potentially also can a methionine residue be approached by a heteroatom from the sort of the same, essentially the same interaction, like a sigma hole interaction?
Yeah, I mean, I have some learnings regarding sulfonamides that these seem to be always that I have a couple of examples in my data set where this didn't work at all. That there was a systematic bias that these would always be predicted to be unfavorable compared to a more hydrophobic group, and this was not the case experimentally. And this was across different projects. I think the thiophene was addressed actually in a recent OPLS update. They made some modifications to that. I don't personally recall an exact example where I observed a large deviation between these different versions.
Okay, thank you.
Next question is from Mandar. Maybe I read it. Can we apply present FEP protocols to RNA drug complexes considering RNA flexibility?
In principle, we can apply it, but as you said, it will be probably very challenging. But I think this will also be something of maybe in the next talk in 5 years that we will be talking about.
So the answer is technically you can if you're very courageous, or?
Yeah, maybe we will also soon see if that works. Let's see.
Shivani, you have a question.
Yeah, hello?
Yes, we can hear you.
Yeah, okay. So have you tried pK calculations using FEP plus, where we want to know protonation or deprotonation free energy of residue? Or is there any automatic tool for which we can make the hybrid topology or setup for these kind of calculations?
Yeah, it's not implemented automatically in FEP plus. Yeah.
Okay, okay. So pK calculations. You also did not do pK calculations?
Yeah, I used the empirical tool for the pKa of the protein. Yeah.
Okay.
But we don't
Thank
do it in a more rigorous way.
Okay, okay. Okay,
Thank you.
Thank you.
And last question from Julie.
Hi, Christina. Thanks. That was a great talk. I wanted to ask if you've used FEP to predict selectivity between two very closely related binding sites to see if you can predict either prospectively or retroactively selectivity. And if so, was it successful at all?
Yeah, we had this situation in obviously a kinase project. In this case, yeah, it's we didn't have much data to compare it to, but there it seemed to work well. But I guess it will also depend on your target.
Yeah, thanks. I was thinking kinases or phosphatases, but that's good to know. Thanks.
Okay, I don't see any further questions, so let's thank both of our speakers again. Thank you very much, Christina and Tony. And please don't dial out. We'll now be magically put by Andreas into virtual breakout rooms. And if you still have a little bit of time, this is a great opportunity to get to know new people, to chat, to ask the questions you maybe didn't dare to ask in the big round. And exactly. So Andreas, will you master and put us into the breakouts? Yes. See you there.